Alright, let's look at the homework 16.3, problem number 6. Alright, so we have a function of three variables. It's a vector valued function, and we want to find its potential. Right, so we can assume that this is going to be a conservative a vector field. Alright, so since this is going to be equal to the gradient of the potential function, we know that this guy right here is going to be partial of the potential with respect to x, and the second component is a partial of f with respect to y, and the third component is of course a partial of f with respect to z. Right? So let's use this guy. So since we know the partial with respect to x is given here, we can take the antiderivative. So f is going to be, we're going to take the antiderivative of the first component, which is yz e to the xz, right, with respect to x. Right? Then antiderivative is going to be, so let's say here, yz is just going to be a number, so I'm going to just put it out here. Right? Antiderivative of e to the xz with respect to x would be e to the xz divided by derivative of this guy, which is going to be z. Right? And plus, right, we could have some function of y and z. So I'm going to put the z of y comma z because we don't know what it is yet. Alright, so we can clean it up and we can see that the z on top and z on the bottom cancel out. So we're going to have simply y times e to the xz plus some function of y comma z. Alright, then we can take the partial derivative of the result with respect to y to make sure that this is going to match the second component. Alright, so partial derivative of this with respect to y would be e to the xz is going to be a number, so e to the xz. Right, and derivative of y with respect to y would be 1, so you just get e to the xz. Right, then you get the partial of z with respect to y, so I'm going to put the partial of g with respect to y. Right, and we have to make sure that this is equal to e to the xz. Right. So which means that we know that here partial of g with respect to y is going to be equal to 0. So it's going to be by taking the antiderivative with respect to y, we know that the g is going to be a function, but then again z is considered to be a constant, so you're going to have g is going to be a constant, so it's going to be a function of just z. Alright, so we have that. Then we have to make sure that the partial of f with respect to z must match the third component. So let's do that. Alright, we take this guy and we take the partial with respect to z. Alright, y is just going to be a constant. Alright, partial derivative of e to the xz with respect to z would be x e to the xz. Right? Then we take the partial derivative of g with respect to z. So we have a g prime of z. Right? So this has to be equal to xy e to the xz. Right? Which means that we know that the g prime of z is going to be equal to 0. By taking the antiderivative with respect to z, we know that the g of z is actually just going to be a constant. So I'm going to put the k there. Alright, so therefore we know the function already. So we have a y e to the xz plus some constant k. All right, so let's type it in. All right, so you're going to have a y e to the xz plus some constant k. All right, so let's go ahead and check the answer. Submit for testing. All right, I came back and looks like we got the part A correctly. All right, so let's look at the part B. All right, part B says that use part A to evaluate this integral here. All right, so this integral here can be rewritten as, so integral over the curve C. All right, this vector field is same as the gradient of the potential. Then we take the dot product with the dr. Right? Then using the fundamental theorem, we know that this is going to be f of ending point. So we have to find the ending point and a starting point. So I'm going to go here. And starting point is going to be r of 0. Right? So you can see that if you plug in 0, you get the 2, comma, negative 2, comma, negative 4. Actually, there's going to be, that's actually 0, sorry. All right, so that's the starting point. Then ending point is going to be when t is equal to 4, so we plug in 4 here. So you have 4 squared is 16 plus 2, 16 plus 2, so it's going to be 18. Right? And here's a 4 squared, so 16 minus 2, so it's going to be 14. Right? So 16 minus 4 times 4 is actually 0. So we have that. So all we have to do is first we plug in the ending point, which is going to be 18, comma, 14, comma, 0. Right? And the minus starting point would be 2, comma, negative 2, comma, 0. Right? So this is going to be, all right, so you have y is 14 and z is 0. So it's actually x component is 0. Right? Oh, actually, I'm sorry, I'm looking at the wrong thing. I have to look at this f, the potential. So plug in y, so you have a 14. Right? E to the xz, z is 0, so it's going to be e to the 0, so it's 1. So 14 times 1, so which is 14. Minus, right? So plug in, let's see, negative 2, so it's negative y, so it's going to be positive 2. Right? E to the, again, z is 0, e to the 0 is 1. So it's going to be 14 plus 2. So answer is 16. Right? 16. All right, so let's type it in. All right, submit for testing. All right, it came back and looks like we got the part B correctly as well. All right, that's it. I hope that this was clear.